Hello everyone and welcome back to Introduction to Number Theory. In this video I would like to give you an example of a Euclidean ring, which is a rather well-known ring, but today we will see why it can be considered Euclidean. Let's consider a ring of Gaussian numbers, Gaussian integers, which I will call complex integers, since it consists of all complex numbers of the form a plus bi, where a and b are simply integers. Well, we know that it is an integral domain, and in order to make it Euclidean, we need a norm. So we use a square plus b square as a Euclidean norm. It is a square of the absolute value of the complex number, but we do not take simply the absolute value, but its square, because we need the norm to be integer. Well, we see that it is non-negative integers. Now, we need to show that for every two complex integers, say w and z, there exist another two complex integers, say, I don't know, y and r, such that w is equal to z multiplied by y plus r. This is division with remainder. R is the remainder, so the norm of r must be strictly less than the norm of z. So w and z are arbitrary complex integers, and y and r, they need to exist. We can prove this in general case, but instead of that, I would like to consider a certain example of w and z and show you how to find such y and r using just your hands, head, and a piece of paper. This is a complex plane, and let this point over here be w, and this point over here be z. We want to divide w by z with remainder. Okay, so let's write down w, and z. W is equal to 1, 2, 3, 4, 5, 6, 7, 8. 8 plus, so its real part is equal to 8. And its imaginary part is equal to 1, 2, 3, 4, 5. And z is obviously equal to 1 plus 3 multiplied by imaginary unit. Okay, so we need to find y and r. In order to do that, let's try to figure out which complex integers can be obtained by multiplying z by all possible complex integers. Well, for instance, z multiplied by 1 is z itself. Z multiplied by 2, just integer number 2, is over here. This is 2 multiplied by z. Well, z multiplied by 3 will go beyond our part of complex plane. Z multiplied by minus 1 will go down. And what about z multiplied by I or minus I, where I is imaginary unit? Well, z multiplied by I will take us over here. Well, not just over here, but z multiplied by I will take us over here somewhere. because multiplication by an imaginary unit is equivalent to rotation by 90 degrees and no change of length, no change of modulus. And when we sum z and z multiplied by I, we will get such a number. So this is z plus z multiplied by I. And I think by this time we already understand that complex integers that can be obtained by multiplying z by other complex integers form a lattice. Let me show you this lattice. We have a point over here, and a point over here, and a point over here. Well, for instance, this complex integer is equal to z plus z multiplied by minus I. So it is equal to z minus iz, which is the same as z multiplied by 1 minus I. So 1 minus I is the complex integer which we use to multiply z. So we continue forming this lattice over here and over here, and the point somewhere over there, and this point, and this point, and so on. I mean, there are infinitely many such points. Now, we see that W appears to be inside one of the squares of this lattice. And we understand that the distance from W to vertices of this square is, well, some of these distances are smaller than the side of the square. Not all of them. We see that this distance is, well, it seems larger than the side of the square. But this one and this one and this one, they are less than the side of the square. And we can take any of these 3 points, not all 4, but of these 3 points, and use it to perform division with remainder. Well, for instance, take this one. Let's say it's case 1. And in case 1, we have that W is equal to Z multiplied by, well, let's see, 1, 2, and minus I, 2 minus I, and plus 3. Simple complex arithmetics. So 3 is the remainder. We can take another point, say this one, case 2. And in case 2, W is equal to Z multiplied by, well, let's see, 1, 2, minus I, minus 2I, 2 minus 2I, and, well, plus I. So in this case, I is the remainder. And we have third case. Where W is equal to Z multiplied by, well, 1, 2, minus I, minus 2I, but plus 1, which means 3 minus 2I, and, well, the remainder here is minus 1 because we need to go left, and minus 2i because we need to go down. So minus 1 and minus 2i. And we see that there are 3 different ways to divide w by z with remainder, and all these divisions are correct. So we do not have the uniqueness of division with remainder. All we need to have is that there exists a remainder such that its norm is less than the norm of z, and obviously the norm of all these 3 complex integers is less than the norm of z. Thus, complex integers form a Euclidean ring.